Good morning all. So today we are going to start a new module on springs. So let me share the screen. So by that we're going to start the session. So springs is one of the important concept in strength of materials too. So the applications of the springs are vast. So they are in many engineering applications, especially for mechanical equipments. So basically springs are basically an elastic bodies, so which are generally made up of metals. So they usually twist. So we can pull them and we can stretch them by the application of force. If you see the member when it is subjected to load, so when you release the load, member will regain its original shape. So that property we call it as a resilience property. So we can call it as strain energy also. In the other words, it can termed as a resilient member. Why? Because when a member is subjected to unloading, so member will regain its original shape and size. So that is a property what the springs usually have. If you see the different classifications of the springs, so I think in the first lecture of springs, we just gone through a few videos. So where you have seen different types of springs like helical springs and leaf springs. So basically helical springs are classified into different categories, like springs which are subjected to tension. So we call it as a tensile helical spring. Where springs are subjected to compression. So we call it as a compression helical spring. Where springs are subjected to torsion, right? They are called torsional springs and spiral springs. So these are the different types of springs comes under helical springs. And the next one is a leaf spring, so which can also be called as a bending spring. So why? Because that spring will be in a form of a plates. So the applications of these springs already gone through in the lecture video 1. If you want, you can go through the video again. So where you can find a number of applications for the springs. Okay. So let me give in brief about springs and all. So basically helical springs are classified into different categories as I told you previously. So which we could call the open coil helical spring, closed coil helical spring, torsional spring and a spiral spring. Okay, so let me give in detail on whiteboard. So what are the springs and how the springs are classified, and springs are comes under which loadings and all we will go in clear way. Okay, right. So let me stop sharing the screen this. Yeah. Okay. So let's start with briefing on springs. So springs may be regarded as a device. So for what? For storing up energy. For storing up energy in a form of a resilience. So resilience is nothing but energy stored in a body. Stored for what? To regain its shape. Okay. So not only storing up energy, it can also be defined as absorbs excess energy. Okay, absorbs excess energy in the sense, so springs, they can absorb energy. So if you see an example, springs which are used in bikes shock absorbers. So they will absorb energy. So by the way, when you go in undulation road, okay, so you can't find that stress. Why? Because springs are absorbing that shocks which are getting through the improper way of the road, right? So in that way we can able to define springs not only stores energy, it also absorbs excess energy. So it all depends upon the function of particular spring under consideration. Okay, so which springs will store energy, which springs will absorb energy. So this all depends on particular springs. So which are based on the consideration in what application you are using. So it is all based on the springs consideration. Okay, so strictly speaking, so all forms of elastic bodies such as struts, ties, beams, they're all etc. So they're all springs as they have resilience property. So why? Because if you take let me write in a new thing. So if you take strut, okay, so if you take tie member, or if you take a beam member, all these members when they're subjected to load, okay, all these members when they're subjected to load, so they will, what they happen, so they will bend. Okay, so due to improper axial load there is a possibility of bending. So when you release the load, again the member will regain its original shape. Okay, there will be an elongation in the member. So when you release the load, member will regain its original shape and size. So by that I can consider all these three members having a resilience property. Okay, so this is a compression member, and this is an tension member, and this is a bending member. Okay, so bending member in the sense beams. Okay, compression member in the sense struts, tension member in the sense ties. Okay, so like this you need to understand what exactly the resilience means. And for all elastic bodies, so I can call all these members as what? Elastic bodies. Elastic bodies. Okay, so as they have the resilience property, but they are too stiff to be used. So why? Because we can divide the springs into majorly two categories. Okay, so springs can be divided into two major categories. One is torsion spring, so where the springs are subjected to torsion. The other one is bending spring. So why springs are called as a torsion spring and bending spring? So where when you see the name called torsion, torsion in the sense member will subjected to twist, okay, with respect to angle. Here bending means member will bend, okay, with respect to axis, with respect to longitudinal axis of the member. Okay, so that's how springs are classified into torsional springs and bending springs. So let's see what do you mean torsional spring and what do you mean bending spring. Okay, so let's see in the new page. Yeah, so first let me write what do you mean torsion spring. What do you mean torsion spring? Torsion spring is the one so which is subjected to what? Which is subjected to twisting moment. Any member or any spring when it is subjected to twisting moment, and the resilience is mainly due to torsion. So here resilience is going to be considered. So it is mainly due to torsion of the member. What do you mean this? Let us take one example of the spring. Okay, so the force which you are applying on the spring is a compression force. Okay, so when you apply the force, what happens to the spring? Spring will compress and it will reduce in its length, isn't it? Right? Reduce in its length. So when you release the load, again spring will come back to its original position. Okay, so here what's happening, from original length to deformed length, spring is reducing in its length due to twisting. Due to twisting only, you can see the reduction in length of the spring. Understand? So why? So because if you take the spring, so spring will reduce in its length with respect to rotation. Okay, it will rotate and it will reduce in its length. Rotation means twisting. So twisting means it is due to torsion of the member. So by that, springs are considered as torsional springs where they are subjected to twisting. Okay, so that is the reason why torsional springs is the one which is subjected to twisting moment. We are considering it as a torsional spring. So the best example for torsional spring is closely coiled helical spring. So closely coiled helical spring is the one, so which is considered as a torsional spring. Okay, right. So next, let's go to the second spring, so which is a bending spring. Let's see the next one, bending spring. Okay, what do you mean bending spring? So bending spring is the one which is subjected to what? Bending. The name itself, it was there, where the spring is subjected to bending, and the resonance is mainly due to bend. So here bend will happen due to resilience of the member. Okay, so the best example for bending spring is leaf or plate spring. What do you mean leaf or plate spring? So let me draw how the leaf spring looks like. So if you see any vehicles, heavy vehicles, right? So near the axle towards the wheel, there will be a leaf spring. Leaf spring will absorb energy and it will distribute the load to the axle. Okay. So the leaf spring will sit on the axle. So through that only the load will be carried to the tires and motor. Okay. So how the leaf spring looks like? How many of you seen the leaf spring which is like this, in this way, right? So this is the how the leaf spring will be there, and the centermost portion you will have a set, so which will rest on the axle. Okay, so this is called the leaf spring. So where these springs will be provided near axle of the vehicles. Okay, so if you see these members, so these members are made up of plates. By the way, so it is called plate spring. So where they are subjected to bend. Okay, so here the bending action taking place in this member. So by that we call it as a bending spring. Okay, so the example of this bending spring is leaf or plate spring. Understood? So next, so which spring comes under both the categories? So there is another spring which is called open coiled helical spring, which will fall under both the categories. Okay, so let me write that also. So there is a third spring which is open coiled helical spring, so which will have both properties. Which one? Torsional and bending properties. Okay, so by that we can call open coiled helical spring as a torsional spring and even a bending spring. Okay, so this is what about different type of springs and the classification of the springs. And the next one, we are talking about stiffness. So the important mechanical property for the springs is the stiffness. What do you mean stiffness? Stiffness is indicated with the symbol K. It can be defined as a load required on a body to produce unit deflection, or a load required on a body to produce unit deformation. Okay, that means load per unit displacement or unit deformation or unit deflection. Okay, we can call in any way. Okay, so if you take a graph between load versus deflection, okay, so the graph of a spring will be always linear. Why? Because linear indicates elastic nature of the member, okay, where P is directly proportional to delta. Okay, so where P increases, your deflection also will get increased. Where P decreases, your deflection also will get decreased. Okay, so we can define your stiffness is always depends on K. Okay, so when the load increases, the stiffness carrying capacity of the member will be always more. Okay, so we can define in other way. When the deflection decreases, your slope will be increased. Why? Because sorry, your stiffness will be increased. That means any spring, if it is having less deflection or less deformation, okay, a spring kanna takku deflection or less deformation undankondi, so that spring will have what? That spring will have more stiffness అని అర్థం. ఓకే, ఏ స్ప్రింగ్ కి అయితే తక్కువ డిఫ్లెక్షన్ తక్కువ డిఫార్మేషన్ ఉంటుందో ఆ స్ప్రింగ్ కి మాక్సిమం స్టిఫ్నెస్ ఉంటుంది. ఓకే, సో దట్ విల్ హ్యావ్ మోర్ లోడ్ క్యారింగ్ కెపాసిటీ. ఓకే, సో దట్ మోర్ స్టిఫ్నెస్ అంటే సో దోస్ స్ప్రింగ్స్ విల్ హ్యావ్ మోర్ లోడ్ క్యారింగ్ కెపాసిటీ. Okay, so that's how that members will have less deflection. When the less deflection, that springs are considered as more stiffness. Okay, so that's what we have to understand the concept of stiffness from the springs. Okay, right. Next we will discuss about closed coil helical spring, which is an example of torsional spring. Okay, so let me discuss that. Yeah, so let's write closed coiled helical spring. So here we are going to take an example of a spring which is subjected to axial pull. Okay, so we are going to take a spring, so where it is subjected to axial pull. Okay, so let me draw the spring. A fixed member with a center axis of the spring. Okay, right. So let me take a spring. So this is the best way of drawing a spring in a 3D diagram. Okay, in 3D. So that's why I'm drawing in this way. Okay. Okay, so where the spring is subjected to axial pull. with the load W. Okay, right. So this is the height of the spring. Height means length of the spring. So the length of the spring can be represented as 2 pi n r. What do you mean n? N is equal to number of turns, or it can also be called as number of pitches. Okay, so where r is equal to radius of spring or coil. Okay, right. So this is what we can able to understand from this. If you draw the if you cut the section here, okay, and if you draw the portion of the spring like this, so when it is subjected to pull, so what happens, there will be an twist takes place with respect to angle of the each ring. Okay, so you can see the deflection of the spring with respect to radius. So here theta can be defined as delta with respect to r. Okay, changing length with respect to radius of the wire. Okay, so this also I need to understand clearly from this. So why this closed coil helical spring is an example for a torsional spring? So here, very important, closed coil helical spring is a torsional spring. Why? Because it is assumed that this type of helical springs are closely coiled. Okay, so then what happens when it is subjected to load? So each turn, I mean each turn and each ring anamata. Okay, each turn is practically a plane at right angle to the axis of the helix. Okay, so if you see the each turn of the member, it is going to make a right angle to the axis of the helix anamata. Okay, if you take this ring is making exactly a right angle to the, this is axis of the spring, axis of helix. Okay, so each ring is making an exactly right angle 90 degrees to the axis of the helix. So by that, and the stresses upon the material is almost, it is in a form of a pure torsion. Okay, so when it is subjected to pull, what happens, each ring will try to elongate with respect to its rotation. Okay, with respect to angle of rotation. When that happens, we should call it as a pure torsion. So that means pure torsion is taking place even in the spring when it is subjected to tensile or compression. That is the reason why closed coil helical spring is determined or termed as a torsional spring. Okay, if you see the relation also, we can able to define the relation very easily, right? So let me draw that here in a new page. What is the torsion, pure torsion equation? Pure torsion equation entama. So let me write this. Pure torsion equation, which is T by J is equal to tau by R is equal to G theta by L. Right? So this is the pure torsion equation. From this, tau is the shear stress, R is the radius of the coil, I mean radius of the shaft. We don't want this. Okay, we will try to relate these two, okay, to frame or to calculate the angle of rotation of the spring. So why? Because when it is subjected to elongation, elongation will always happens with respect to theta. Okay, just now we have drawn this, right? So if you take the spring when it is subjected to pull or push, so there will be deformation taking place with respect to the radius. So here theta is defined as like this. Okay, so in this way, from this relation, okay, from this relation we can write T by J is equal to G theta by L. Okay, so what is theta here? Theta is the angle of twist. Theta is the angle of twist at the end, isn't it? So next, so take theta out here. So why? Because this relation can be written as pi d power 4 by 32 is equal to g theta by L. Okay, so finally this can be written as theta is equal to T L by G pi by 2 d power 4, isn't it? So what is this? This can be written as 32 W. What do you mean W here? What is W? How you got this W? So because here torsion is equal to load with respect to radius. Understand? So why? Because in torsion you have seen the shaft, a circular shaft, when it is subjected to pull with respect to radius. So here T is equal to P into R. Even in the springs also. Okay. So when it is subjected to load W, the torsion is taking place load with respect to radius of the coil. Okay, load into, W into R, which is nothing but torque of the springs anamata. Okay, so by that this can be written as 32 W R into L. What do you mean L? L is nothing but length of the spring, pi d power 4 into N. So finally, this theta can be written as T is equal to 32 WR. What do you mean L? L is the length of the spring. Length of the spring can also be denoted as 2 pi NR. What do you mean 2 pi NR? 2 pi NR is the total length of the spring with respect to the number of turns and radius of the coil by N pi. So this is pi d power 4. Okay, so this can be written as finally 64 W R square into N by N d power 4. Clear? So this is the final equation, final relation to calculate theta of the spring. 64 W R square into N by N d power 4. Right? So this is very important to calculate theta, to calculate angle of twist or angle of rotation of the spring. Okay, so by that, from this relation, what I understood, very important statements I would like to write here with respect to this angle. So let me write note. What is note here? Free end will twist through an angle theta consequently. So the free end will have an axial moment. Okay, so what happens when it is subjected to angle theta? So free end will have an axial moment, so which is R into theta. Okay, so what happens if delta is nothing but displacement? If delta is the axial moment or deflection of the free end, we have the delta can be written in another relation. Okay, so those points we are going to discuss in the third module, third lecture. Okay, so which is the continuation of the closed coil helical spring. Okay, so that we are going to discuss in the next class. So here, apart from this, I would like to tell you three relations. So three important things where the shear comes into picture. Okay, so let's take a solid object, right? When it is subjected to shear, how it get deformed? So it will deform like this. So we call it as a distortion. So there will be change in length with respect to height of the member. So then how this shear strain can be written as? This pi shear strain can be written as delta L by H. So this is for solid objects, isn't it? So let me see for shafts. So shafts are also subjected to twist, right? So why the shear modulus or modulus of rigidity comes into picture in the shafts? So let's take a shaft. Okay. So when it is subjected to twist, what happens? So member will deform from one position to other position. Okay, with respect to center. Avuna? So from A to A dash. Okay. So from A to A dash. So what is this? This is the radius of the member. Okay, so this is the length of the shaft. So here, how you define this? How you define this pi? So here pi is the shear strain. Pi is equal to A dash with respect to length of the member. Okay, this is the shear strain of the shaft where the shift taking place from A to A dash with respect to length of the member. Okay, so this is how we can define shear stress in the shafts. So coming to springs, how you define in the springs? How the shear comes into picture in the springs? So let us take a spring. So when it is subjected to compression, okay. So this is the axis, right? So this is the radius. So if you take in deep radius, so when it is subjected to compression, there will be change in its height of the each pitch. So this we call it as a pitch. So this pitch will try to reduce, so that we call it as a deformation of the member. Okay, so where the angle of rotation taking place. So theta is the shear strain here, so which can be defined as displacement with respect to radius of the member. So this is the shear strain in the springs. So this is the shear strain in the solid objects. Okay, so this is the shear strain in the shafts, and this is the shear strain and the angle of rotation or angle of twist in the springs. So that's why in all these three, shear comes into picture. So shear ante enti? Shear ante what we call shear here. Shear means distortion. Okay, distortion or sliding from one position to other position. Okay, so this is how we can define springs with respect to shear aspect. Okay, so this is what about closed coil helical spring. So in the next class we will continue with the deflection, how to calculate a deflection of the springs delta, because we have derived a relation for the springs in terms of theta, isn't it? So we have calculated theta here. I mean, we framed a formula for theta. In the next class, we will try to define what is the deflection, how to calculate delta, okay, of the closed coil helical spring. Okay, right. So thank you so much. So please watch for the next video. Okay. Yeah. Okay, right. Thank you so much. So please be watch all videos, so which can be taught for the springs as well, right? Okay, ma'am. Thank you. Bye.